In this video, we're going to work some examples of arc length problems. It's actually pretty simple. We tend to just use these two formulas and substitute into the appropriate formula. I've also graphed the functions on desmos.com and looked at the graph just to see kind of what's going on here. But the graphs themselves aren't really that insightful. In practice, all I'm going to do is take the appropriate derivative. If y is a function of x, I'm going to use this one. If x is a function of y, I'm going to use this one. Sometimes it's ambiguous, or sometimes you can write it both ways. You could write x as a function of y or y as a function of x. You could use either one, and either one will give you the right answer. But most of the time, the problem is posed in such a way that it's sort of obvious what they want you to do. So here I've got y as a function of x. I'm told that x starts at 0 and ends at 3. And if I look at the curve, this is what it looks like. Since I'm given bounds for x and I'm given y as a function of x, I'm just going to use that top one. So it's actually extremely simple. All you have to do is find y prime and substitute into the formula, and then evaluate the integral. Now, there's a lot of algebra that tends to go into simplifying something like this. If y prime was just x, like the derivative of our function was simply x, well then you've got a 1 plus x squared under a radical, and now you have to do a trig sub all of a sudden in order to evaluate that integral. So it's very, very easy for these integrals to be complicated. Now the textbook authors have tended to be relatively nice in the way that they've derived these problems for us to solve. Most of the time, the problems that we're going to be solving with arc length involve a lot of algebra, so that this is a perfect square, and we're taking the square root of a perfect square, and we can get rid of it, get rid of the perfect square with the square root. So they're pretty contrived so that that happens, or they're contrived so that a u substitution happens often. We will also look at a couple of problems that require some of the more advanced methods from Chapter 8. But we're going to start out with some of the problems in this section that just involve finding the length using the formulas. So I'm going to use the top formula. Since y is a function of x, I have the integral from a to b of the square root of 1 plus y prime squared multiplied by dx. So I'm just writing this to set it up. Now, you can't just call that 1 plus y prime. You can't just take the square root of each piece. This is not equal to a plus b. That does not work that way. So please don't tell me that's 1 plus y prime, because it's not. You can just plug in a couple values for a and b, and you'll see most of the time that this is not true. This is not generally true. So don't do it. Don't try to take the square root of each piece and then just add them, because it doesn't work. What you're going to have to do instead is compute y prime, find out what that is, square it, add 1, and then hopefully that simplifies to something that we can integrate. Now x equals a and x equals b are where we start and we stop. So that's a and that's b. A is 0, b is 3. On our curve, here's 0 for x, and then 3. And then we need y prime right here. To take the derivative of this function, we have to use the chain rule. So we've got this is nested inside this other function. I've got 1/3 times a function to the 3/2. The derivative of 1/3 times a function to the 3/2 is 1/3 times the 3/2 times that function raised to the 3/2 minus 1. 3/2 minus 1 is 3/2 minus 2/2. 3/2 minus 2/2 is 1/2. And then you plug your inside function back inside. Don't do anything to it. Just sub it back in. And then you multiply by the derivative of the inside by the chain rule. And the derivative of the inside is derivative of x squared, which is 2x, plus the derivative of 2, which is 0. So the 3's reduce. This 2 and that 2 reduce. So we just end up with an x times the square root of x squared plus 2. That's what we've got here. X times that square root. Now we're going to square it before we integrate. This looks kind of ugly, doesn't it? It looks bad, but hopefully through some algebraic manipulation, this will be something that we can, some integral that we can evaluate. So we just identified a and b, we plugged in the derivative, and that's our integral. Now we just simplify so that we can find the length of the curve. Now this is a product. I've got something times something else squared. So remember, if you've got a times b squared, that's the same as a squared times b squared. Don't forget that. Well, it's okay if you do. If you do, I'll remind you. But that's my a and that's my b. So I'm going to have an x squared there, and the square root, the squared, is just going to leave me with what's under this radical. So if I've got the square root of a squared, if a is positive, we just get a back. And x squared plus 2 is positive. So I'm just going to get an x squared plus 2 there. And we're integrating with respect to x. Now it still doesn't look like something I can evaluate. So we're going to distribute that x squared. We've got x squared times x squared is x to the 4th. And x squared times 2 is 2x squared. Oh, I'm seeing something. Are you seeing it? If you're not seeing it, that's okay. I'm going to rewrite this in a slightly different order. Let's write these in descending powers of x with the highest power of x first, then the next lowest power of x, and then that constant is last. Do you see it now? That's a perfect square, guys. You might say, how do you know? Well, it factors. Watch this. First times first has to be x to the 4th. So if I've got an x squared here and an x squared here, x squared times x squared is x to the 4th because we add the exponents. Now, outer times outer is going to be something times x squared, and inner times inner is going to be something else times x squared. So outer times outer plus inner times inner could theoretically give me that 2x squared if I pick the right numbers. And last times last could give me a 1. So just ask yourself, well, what two numbers add to give you 1, or multiply to give you 1 that adds a 2? Hope you said 1 and 1. And check, make sure that this actually turns out to be this, FOIL. First times first is x to the 4th. Outer times outer is 1x squared. Inner times inner is another x squared. So I've got 2x squareds. And then last times last is 1. That's nice, guys. You see it? You see it coming? That is x squared plus 1, quantity squared. What's the square root of something squared? We just did it. It's just going to be the x squared plus 1. Isn't that nice? I think it's nice. Textbook authors were nice to us. They made this problem where it worked out just perfectly. And now, this ugly thing that we started with simplifies to this beautiful thing, this very easy thing to integrate. So we're going to finish our problem by anti-differentiating, add 1 to the exponent, divide by the new exponent. The antiderivative of 1 is just an x. Then plug in 0, plug in 3, and subtract. You're going to have 1/3 times 3 cubed plus 3. That's evaluated at 3. And then if I plug in 0, I just get 0. So this is 27 over 3, which is 9 plus 3. So we get 12. That's the length of that curve. You're saying, what do you mean that's the length of that curve? That means if this is 1 unit and I were to go 1 unit, 2 units, 3 units, and just going length, one piece at a time, one foot at a time, 1 meter at a time, 1 unit at a time. Turns out there are 12 of those units there. It's 12 units long. If we were walking along that path, if this was in miles, it'd be 12 miles long. If that was 3 miles and that was 12 miles, our path here would be 12 miles long. Okay, so that's the first example. Literally all you're doing is identifying a and b, finding the derivative. And then there's a lot of algebra. Often it simplifies to something you can integrate. Then you integrate using the fundamental theorem of calculus, and that's giving you the length of this curve. All right, next example. This picture is not as good, but it's roughly like that. I've got x as a function of y. We've got a 1/3, or y to the 3 halves divided by 3, minus y to the 1/2. and we're integrating from 1 to 9. Now, since I've got x as a function of y this time, I'm going to use this formula. We tend to use constants c and d instead of a and b when we're integrating with respect to y. It's just convention. We could use any letters we want there. We're just going to use this time. And c and d are the bounds for y. So y starts at 1, excuse me. That's our c. And y ends at d, that's our 9. So from y equals 1 to y equals 9, we want the length of that curve. C and D. So I put in my 1, I put in my 9. Now this time, because I've seen problems like this before, I'm not going to do the algebra inside the integral, because I know there's going to be a lot of algebra to simplify this thing. Instead, I'm going to simplify the integrand first, and then I'm going to substitute the whole integrand. So let's do this. First, I've got x equals this. Do you see that that is a 1/3 multiplying that y to the 3/2? If you don't believe me, write this y to the 3/2 as itself over 1, and you multiply straight across, right? Don't you get that? So that's another way of writing the same thing. X is just 1/3 y to the 3/2 minus y to the 1/2. Now, according to our formula, I've got to take the derivative of x, I've got to square it, and I've got to add 1. So first I'm going to take the derivative. This is just the power rule. So we bring our constant down, and then you've got y to some power. The derivative of y to some power with respect to y is that power times y to the 1 less power. 3/2 minus 1 is 1/2. And then here, bring the negative down. And then here I've got y to some power, bring the power down, multiply by y to the 1 less power. 1/2 minus 1 is negative 1/2. And the 3's reduce, and we just get a 1/2 y to the 1/2 minus 1/2 y to the negative 1/2. Now notice that those exponents have opposite sign. It's a y to the n and a y to the negative n. There are a bunch of problems in the textbook that have follow this pattern. It's a little bit contrived. They're trying to find functions that you can take the derivative of so that the x prime squared plus 1 or y prime squared plus 1 simplifies to a perfect square, and you can take the square root and you get this beautiful answer, or beautiful integrand. One type of function that works like that is this, where you've got y to some power and y to the opposite power. And you're adding those, or you're subtracting those here. So you're going to see that pattern a lot as you go through the homework. And there's a lot of algebra in this, I'm just warning you, but it's exactly the same algebra every time. So if you can start to see the pattern, then hopefully it won't be too bad. Okay, so let's go to our integrand and simplify that. The integrand was the square root of 1 plus x prime squared. So I'm going to put that square root on last. I'm going to say 1 plus x prime squared is 1 plus 1/2 y to the 1/2 minus 1/2 y to the negative 1/2 squared. So I'm going to write that twice and FOIL. You could have factored out the 1/2 if you want to. I find students do better if they don't, because they make algebra errors if they do. So first times first, 1/2 times 1/2 is going to give me a 1/4. And then I've got y to the 1/2 times y to the 1/2. Add the exponents, it's going to be y to the first. Outer times outer, you've got a positive 1/2 and a negative 1/2, so that's negative 1/4. Y to the 1/2 times y to the negative 1/2. Remember, you add the exponents. 1/2 plus negative 1/2 is 0. Y to the 0 is 1. So So y to the 0, just multiplying the negative 1/4. So you just get a negative 1/4. These guys are the same. You got a negative 1/4. Y to the negative 1/2 times y to the 1/2 is still y to the 0, which is still 1. And then last times last is a negative times a negative, which is a positive. 1/2 times 1/2 is 1/4. And you want to add those exponents. Negative 1/2 plus negative 1/2 is negative 1. Now I want you to see something here. Watch this. The negative 1/2, or negative 1/4 minus 1/4 is negative 2/4, or negative 1/2. So before we go any further, I just want you to see this quantity in parentheses. That's this. That's just x prime squared. X prime squared gave me this. First times first gave me the 1/4 y. Last times last gave me the 1/4 y to the negative 1. And inner times inner plus outer times outer gave me that negative 1/2 in the middle. And when I factor that, this factors to that. That's my first term, that's my last term, and there's a minus there. And that led to the minus 1/2. Now I'm going to add 1 to that. 1 plus the negative 1/2 is going to give me a positive 1/2 in the middle. Now, it might not be obvious that this factors. I might look at this and say, well, why would I even think that that factors? Here's why I would think that that factors. Because it looks just like this. But this one has a minus sign and that one has a plus sign. I say to myself, well, if that has a minus there and that had a minus there, I bet if I do exactly the same thing that we have there, a 1/2 y to the 1/2 and a 1/2 y to the 1/2 and a minus, and then the last times last is 1/2 y to the negative 1/2 and 1/2 y to the negative 1/2. But instead of having a minus there, I bet if I have a plus instead, it's going to give me this. And you should check and make sure it works. First times first is 1/4 y to the 1/2 plus times y to the 1/2. Add the exponents, y to the first. Good. Outer times outer, they're both positive this time, so that's a positive 1/4 y to the 0, which is 1. Inner times inner is another positive 1/4. 1/4 plus 1/4 is that 1/2 in the middle. Last times last is exactly what it's supposed to be. So this is 1 plus x prime squared. I've got 1/2 y to the 1/2 plus 1/2 y to the negative 1/2 squared there. The integrand is the square root of that. So it's the square root of this, which is the square root of this, which is the square root of this. I'm just going to put my square roots in everywhere so that's actually equal to each other. And watch this. This is always positive. If I take the square root of something squared, I'm just going to get that back. You might say, what? Yes, that's what happens on these problems where you have the y to the n and a minus and a y to the negative n, or an x to the n and a minus and an x to the negative n. The textbook authors generated these in such a way that every time I square this and add 1 to it, I get a perfect square. And this perfect square is very similar to that perfect square. That one had a minus, this one has a plus after I square that and I add the 1 to it. Now you should check every time to make sure that this actually happens. You should go through and do this algebra. But if you see this pattern, that's probably the pattern that you're going to see over here. So that's our integrand. So this thing that we're integrating can be replaced by this. Okay, so I think we're ready to evaluate our integral. We have s equals the integral from 1 to 9 of the square root of 1 plus x prime squared dy. And the square root is this. 1/2 y to the 1/2 plus 1/2 y to the negative 1/2. We're integrating with respect to y. Bring the 1/2 down. Add 1 to the exponent and then divide by the new exponent. Dividing by 3/2 is multiplying by 2/3. Bring the 1/2 down. Add 1 to the exponent and divide by the new exponent. Dividing by 1/2 is multiplying by the reciprocal. Multiply by 2 over 1. Substitute 1 and 9 and subtract. That's the fundamental theorem. The 2's reduce here, the 2's reduce here. So you've got 1/3 times 9 to the 3/2 plus 9 to the 1/2 minus 1/3, 1 to the 3/2 is 1, plus square root of 1, or 1 to the 1/2 is 1. That's our answer. It's just not simplified. But remember what this means. If you've got x to the m over n, so x with a fraction in the exponent, this is the index of the root. So we're taking the nth root of x to this power. Or if you wanted, you could take the nth root first and then raise the whole thing to the mth power. Either one is fine. Now, if I'm simplifying numbers like this, I've got a number raised to a rational exponent like that, I probably want to do this because taking the nth root makes it smaller, and then I'm taking a small number and raising it to a power, as opposed to taking a number, making it large, and then trying to think about what the nth root of that would have to be. Like, this is usually easier for your mental arithmetic. So I'm going to think of this as the square root of 9 quantity cubed. And that's just the square root of 9. And that's 1/3 plus 1, that's 4/3. All right, square root of 9 is 3. 3 cubed is 27. 3 cubed divided by 3 is, of course, 3 squared, or 9. Square root of 9 is 3. And so we've got 12 minus 4 over 3. So that's going to be 36 over 3 minus 4 over 3, which is 32 over 3. And you say, what was that again? What on earth are we doing? That's the length of this guy, the length of this curve. The curve that's given by this x is a function of y, for y between c and d. Now you see it's a little bit contrived. I've got y to some power here and y to the negative power. It turns out whenever you've got those powers that have the same magnitude but opposite sign, that's y to the n and y to the negative n, when you square that and add 1 to it, pretty much every time, you're going to get that perfect square that simplifies. Gives you that. That's your integrand. And then you just use the power rule to anti-differentiate in the fundamental theorem of calculus to get that final number. So those are 2 examples of arc length. This one required the chain rule to take the derivative, but it also worked out to be a perfect square. Now, they don't all work out to be perfect squares. Sometimes they work out to be problems that require u substitution, and be prepared for those as well. I'll do examples like that in the next video.